Good morning, friends. I hope you are doing well amid this lockdown situation and you have gone through the lectures of root locus. So in this particular tutorial, in this first tutorial lecture, we will see some numerical based on the concept of root locus. These are very important in nature. In the first part of this, I will go through some questions and take your time to solve this, and in the next part, we will discuss the solution of these questions. So let us move towards control system tutorial part 1, which deals with numericals on root locus. So the requirement for this particular tutorial will be these 4 lectures. These are basically the pre-requirements, namely CS-21 basics of root locus, CS-22 and 23 rules of root locus construction, and CS-24 numericals on root locus step by step. Only if you have finished these 4 lectures, you can proceed to solve these numericals. Right? So here is your first numerical. It says that so that the root loci for a control system given with a given GS and given HS is a circle with center -1, 0 and radius small r root 2. So how you will approach this particular numerical? You are not required to draw any root locus for this particular question. You need to approach this question analytically. So what you will do means, what does this question means? First, let us understand. Here we are having our sigma axis is a horizontal one, and this one is our j omega axis, vertical one. And what this question says? This question says that prove that the root locus for a given system is basically a circle with a radius having center -1, 0. So let us first try to draw how it will look like. Here is your -1, 0 point, and if you will draw this circle according to the question, then it will look like something this one, this one, with a radius is equal to r is equal to root 2. Clear? So though you are not required to draw any diagram, you have to prove this question analytically, but for the sake of understanding, I have drawn this particular diagram. How you will approach this question? Well, you know the value of S anywhere. S is what? S is a point in this complex plane, means sigma and j omega plane. So what will be the value of S? The value of S will be basically sigma plus j omega. So replace every S by this sigma plus j omega, apply some condition and try to prove this is a circle. Basically the root locus is a circle, right? Means you need to derive the equation for circles. Coming to the next question. Second question says that sketch the root locus plot with k is a variable parameter in the previous question, means question number 1. Is the system stable for all values of k? Means it is asking whether the system is stable for all values of k or for some particular values of k. So if the system is not stable for all values of k, you have to proceed further. You have to determine the range of k for stable system operation, right? So if it is not stable for all values of k, there might be some range of k for which that system will remain under the boundary of stability. Clear? Find also the marginal value of k, right? What will be the marginal value of k? Which causes sustained oscillation. I said that if the system is not stable for all values of k, it will remain between two threshold points. So those threshold points on either side, you have to look for those threshold points on which sides, either left side or right side, will give you the marginal value. And from graphical approach, you can say that if you are having a, say here it is say if you are having a j omega axis like this, sigma axis like this, sigma and j omega axis, and suppose root locus of something is like this anyway, and this type of thing, right? It is going like this. So what can you say about this? Here is a pole, here is a pole, for example I am saying, and the root locus, when the value of k increases, the roots will move like this, and at a particular value of k it will be at j omega axis, and if the value of k will be greater than that particular value of k, the root will go beyond j omega axis towards right side of the S plane. When it will move towards the right side, means this side, RHS, right hand side of the S plane, the system will become unstable. So it will remain stable till here, right? Means k, you are going to vary k from 0 to infinity, because by default that we draw the root locus for the variation of k which lies between 0 to infinity. But for infinity it will go like this. Okay, the system will become unstable, and here the system will oscillate with a certain frequency, right? So you need to calculate this value of k if it exists. Otherwise, if it doesn't exist, if certain root locus is something like that, say a certain root locus is like this, so it will be stable for all value of k. It is not going to say here it is it is not going to cross this boundary, and it is not going to fall on the right hand side, right? So it will be stable always. So you have to see whether it is stable for all values of k. If it is stable for all values of k, you say that okay, it is stable for all values of k. If it is not stable for all values of k, find the range of k for the stable operation. Also find the marginal value of k. Marginal value will be that value of k and for which the root locus will be at j omega axis. Okay, and that value of k, of course, since it is at the verge of instability, it will cause some sustained oscillations, and you need to find the frequency of these oscillation also. How come you will find the frequency of these oscillation? Well, note that the y-axis is j omega axis, where omega is a frequency. Sufficient hint, we will solve in the next session. Try it. Okay, part B is that from the root locus plot, determine the value of k such that the resulting system has settling time of 4 seconds. So recall the formula for settling time and try to find this value of k. What does the next question says? It says that for a linear feedback system for a given with a given GS and a given feedback transfer function HS, sketch the root locus when the gain is varied from 0 to infinity. So we know that the gain can vary in two ways. Okay, it can be from 0 to infinity, and when it is from 0 to infinity, you say that it is direct root locus, right? And when the gain varies from minus infinity to 0, you say that it is inverse root locus. Clear? And if it is not specified in the question and you are being asked to draw the root locus, you will always draw the root locus, direct root locus, for which the gain varies from 0 to infinity. Here it is already specified that you have to draw the root locus when the gain varies from 0 to infinity. Clear? So we always draw direct root locus unless until specified in the question to draw inverse root locus. Clear? Coming to the next question. So draw it on the graph paper. The open loop transfer function is given by some expression is given for GSHS. Sketch the root locus when the gain is varies from 0 to infinity. Once again, you have to draw a direct root locus for which gain varies from 0 to infinity. For semester point of view, you will be always asked to draw direct root locus. Clear? Coming to the next question. What it says? It says determine the open loop transfer function from the given root locus plot shown below. Okay, graph is not shown below, so I am drawing it. Here is your sigma axis. Here is your, I am going to say it is j omega axis. Imaginary axis, this is also called as real axis, and this is imaginary axis, right? You might be knowing. What else is given? And it is shown like a pole at 0 is there. It is 0. One more pole at -1 is there, and one more pole at -2 is there. And the root locus, since if you recall the rule of root locus, when there is a pole at the leftmost part, and if that part is a part of root locus, it will move like this. So this is given, already given. And this portion between 0 to -1 is a part of root locus. This is a part of root locus. So here will be a breakaway point. It is also given, and this point is given like this. Clear? So this is given to you. This value of this point is also given. This is 1.414 J, and correspondingly it is symmetrical -1.414 J. Clear? So determine the open loop transfer function from the given root locus plots, right? And this given root locus plot is here. The red part shows the portion of root locus. Determine the range of K for stability, right? What could be the range of K for stability? That value of K will start varying from 0 to infinity, but when at a particular value of K is equal to K marginal, it is going to cross this j omega axis. So for any value which is greater than K is equal to K marginal, the system will become unstable. So you have to find the value of K such that the system will remain this side, only this side, right? Also find the forward path transfer function if Hs is equal to this one. Forward path transfer function means what? Gs. You have to find the value of Gs also. Clear? So attempt this question. You will see the solution in next part. And this is the last and final question. Here open loop transfer function of a feedback system is given, and you need to sketch the root locus for this particular system. This is, I think, the most important question in this tutorial as far as tracing the root locus is concerned. So try to attempt this particular question, and we will see the solution in the next tutorial. What is next? Next, keep on studying. We'll meet in the next tutorial. Thank you.